The biggest shift this week is that AI is getting better at structure control, not just generation. Editing video with precise temporal coherence, segmenting dense cell fields with almost no annotation cost, and turning raw multi-view images into editable 3D objects. That matters because the bottleneck is no longer only model quality, it's data efficiency, interaction cost, and whether the model actually understands parts, instances, and motion. The common thread is foundation models becoming more usable in real pipelines. Keep watching, because the details reveal how much of that progress comes from smarter supervision, not just bigger models. Let's explore the first paper, Goku, a million scale, universal dataset and benchmark for instruction-based video editing. Goku, developed by the University of Science and Technology of China and Tencent Hunyuan, pushes instruction-based video editing beyond narrow appearance, transforms by releasing a 2 million pair dataset that explicitly covers basic edits, camera movement, subject movement, reference-guided editing, and 2-5 task multi-edit compositions. The paper's synthesis pipeline starts from 1 million koala, 3.6M clips, then uses Gemini 2, 5 Pro for instruction generation and progressive filtering, Grounded, SAM2 for temporal masks, Vase, Flux, Minimax Remover, WAN 2, and Recam Master for task-specific synthesis, and discards about 88% of synthesized candidates to preserve alignment, temporal stability, and photorealism. On top of this data, the authors propose Goku Edit, a dual-branch model built on WAN 2, 25B with a frozen Qwen 3 VL, 8B MLLM text encoder, a dedicated mass prediction branch, Ropie-aligned spatial cross-attention, and spatial CFG for stronger structural control. They also introduced Goku Bench, a human-verified benchmark with 1,000 test cases and 7 metrics spanning physical rule, fidelity, spatial accuracy, instruction following, and task-specific subject motion, camera motion, and style transfer. On Goku Bench, Goku Edit delivers up to an 8% gain in instruction following over other open-source models. And ablations show that Goku scaling, filtering, and the spatial modules all contribute measurably to the final performance. Let's explore the second paper, One Click Per Cell, Type Suffices Training, Free Group Interaction for Cell Instance Segmentation. This paper introduces Chain of Prompts, a training-free interactive framework built on the frozen image encoder of SAM3 that changes cell instance segmentation from 1 click per instance to 1 click per cell type. The key insight is that SAM3's encoder already clusters same-type cells in feature space before prompting, so the method uses hierarchical similarity gating to combine high-resolution and low-resolution cosine similarity maps, then applies non-parametric thresholding and connected component labeling to extract reliable prompt points with precision above 96%. Farthest prompt recursion then selects the next prompt as the spatially farthest unreached reliable point, recursively expanding coverage without learned parameters. On 3 cell-type annotated benchmarks, Conic, Concept, and Glass COP with only about 3 clicks per image, retains over 90% of per instance SAM3 performance, while cutting annotation costs by 97% and even surpassing fully supervised models such as CellVit, CA, SAM2, and CellPost 3. On 4 morphologically homogeneous benchmarks, MonuSeg, TNBC, CryoNuSeg, and CPM, 1.7, a single click per image, preserves over 99% of per instance prompting performance. The ablation study shows that removing recursive propagation drops AJI from 0.579 to 0.203, while the full method reaches 92.7% of the upper bound AJI in an example with 3 clicks versus 245 per instance clicks, demonstrating that group prompting is a practical way to scale foundation model interaction to dense histopathology images. Let's explore the third paper, Scenes as Objects, Not Primitives. Instance, Structured, 3D Tokenization from Unposed Views. Scenes as Objects, Not Primitives proposes a feed-forward 3D reconstruction framework from unposed multi-view images that represents a scene as instance-structured 3D token groups rather than dense per-Gaussian primitives. Built on the pre-trained VGGT geometry foundation model and evaluated on ScanNet, the method uses an image anchor transformer to decode anchor tokens that spawn 3D Gaussians, then an anchor grouping transformer to produce instance tokens that compete for anchor ownership via softmax assignment. Training relies only on 2D supervision, RGB rendering loss for reconstruction, and Hungarian-matched instance mass supervision for grouping, with no 3D annotations. The key novelty is a 2-level semantic factorization. Each instance stores a shared 512 dimensional group embedding, while 8 dimensional anchor residuals capture local variation, reducing feature storage from 8 4M scalars in Uni 3R to 59 4K. On ScanNet with 2 context views, the model reaches 0.661 source view MIOU and 0.657 target view MIOU for feature lifting, while keeping reconstruction competitive at 25.28 PSNR, 0.771 SSIM, and 0,2 opt LPIPC. With 8 context views, it achieves the best class-agnostic instance segmentation, reaching 0.235 AP, 0.438 AP50, and 0.564 AP25, outperforming per-scene optimization baselines such as Gaussian grouping and Object.js. The same token, groups also enable direct instance-level editing and open vocabulary retrieval, and the paper reports zero-shot transfer to MIP-NERF 360 and robustness on real estate 10K using SAM2 pseudo-labels. That's a wrap on today's AI paper highlights. Thanks for watching.